Hey everyone, welcome back for another deep dive. You guys sent in some really awesome sources on radiative cooling for this one.
Yeah,
And I am so pumped to get into it.
me too.
We've got scientific papers, news articles,
Oh, wow.
the whole shebang.
Nice.
Which is great because we're actually tackling not one, but two groundbreaking technologies.
Yeah, multiple perspectives are always key for understanding these complex topics. So let's unpack them.
Yeah, let's get into it.
The first technology is all about making buildings more efficient.
Okay.
And the second one, well, it's actually generating power from the coldness of space.
Generating power from coldness.
Yeah.
Okay, you definitely have my attention.
Yeah.
But before we get to that science fiction stuff, let's start with the basics.
Okay.
What exactly is radiative cooling?
Right.
I know it's a natural thing,
Yeah.
but I'll admit I don't fully get it.
Sure. So it's actually something we experience all the time, especially on clear nights.
Okay.
Think about how things get dewy, even if the air isn't that cold.
Right.
That's radiative cooling in action.
Right.
Okay. Basically, the Earth is constantly losing heat to space as infrared radiation. It's like our planet has an invisible exhaust pipe sending out heat energy towards the freezing vacuum of space.
So even when it's a warm day here, our planet is sending out heat energy upwards.
Exactly.
That's wild.
And there's a specific wavelength range where this heat escapes most easily.
Okay.
It's called the atmospheric transparency window,
Hmm.
and it's between 8 and 13 micrometers.
Okay.
Think of it like a special channel where infrared radiation can pass through the atmosphere with almost no resistance.
Okay. That makes sense. So is that why cloudy nights tend to be warmer? The clouds are kind of blocking that window?
That's a great observation.
That's
You're
fair.
exactly right. Clouds
Okay.
can act like a blanket, trapping some of that heat radiation and preventing it from escaping to space.
So on a clear night, a building or a car, anything really,
Yeah.
is sending out heat through this window and cooling down.
Yeah.
Even if the air around it isn't that cold.
Exactly.
And scientists are figuring out ways to use that to our advantage.
Precisely. Now, imagine we could enhance this natural process,
Okay.
making things cool down even faster and more efficiently.
Right.
That's where these two technologies come in.
All right, let's get to the good stuff.
Let's do it.
First up, we have something called cooling wood.
Okay.
The article you sent from Science in 2019 had me hooked from the first paragraph.
Awesome.
They basically engineered wood to act like a super radiator.
It's a really ingenious process.
Yeah.
They start with regular wood and remove the lignin, which is a component that gives wood its rigidity.
Okay.
What's left are mostly cellulose nanofibers,
Okay.
and they compress those fibers to create this incredibly dense, strong material.
So they're basically making a super version of wood.
Yeah,
And this super wood is designed to maximize radiative cooling.
exactly. Cooling wood is designed to be both white to sunlight
Mm-hmm.
and black to infrared radiation.
Okay.
That might sound strange,
Yeah, a little bit.
but it's the key to making it cool down.
Okay, I'm intrigued, but my brain needs a bit of help here. How can something be both white and black at the same time?
Think about it this way.
Okay.
Being white to sunlight means it reflects most of the visible light hitting it.
Right.
Kind of like how a white t-shirt keeps you cooler on a sunny day.
Yeah.
But being black to infrared means it's really good at releasing heat energy as invisible infrared waves, which is exactly what we want for cooling.
Ah, that makes sense.
Yeah.
So it's reflecting the sunlight we can see and emitting the heat we can't see.
Right.
Clever. But the article also mentioned the structure of the cooling wood itself plays a role.
Yeah,
It's not just about color.
you're right.
Okay.
The multi-scale fibers and channels within the cooling wood are crucial. They help to scatter sunlight even more effectively, further boosting its reflectivity.
So it's like this super reflective, super emitting material.
Exactly.
Did they actually test this stuff out in the real world?
They did. The researchers conducted field tests in Arizona, which is known for its intense heat.
Right.
And the results were impressive.
Yeah.
Even in the scorching Arizona sun, the cooling wood stayed significantly cooler than the surrounding air.
Okay, that's seriously cool. Literally.
Oh.
They essentially create a passive cooling system using the sky itself.
Right.
I'm already imagining buildings with roofs and walls made of this stuff.
Yeah.
Cutting down on AC costs like crazy.
Absolutely.
But hold on, the article also mentioned something about this cooling wood being incredibly strong.
It is. The researchers found that cooling wood is much stronger and tougher than natural wood.
Okay.
What's even more remarkable is its strength-to-weight ratio, which actually rivals many metals, including steel.
Wow, that's amazing. This is starting to sound less like wood and more like some futuristic wonder material.
I know, right?
It's eco-friendly,
Yeah.
it's energy efficient,
Yeah.
and it's super strong. Okay, I need a moment to process all of this
Sure.
so we could use radiative cooling to passively cool buildings.
Right.
But what about, actively generating power?
Okay.
You mentioned something about that earlier, and I've been dying to hear more.
That's where the second article comes in.
Okay.
And it's a real head-scratcher.
Okay.
Researchers actually built a device that generates electricity using the cold night sky.
Wait, hold up.
Yeah.
You're telling me we can create power from coldness. How is that even possible?
It seems counterintuitive.
Yeah.
But remember, heat engines don't necessarily need scorching heat to work.
Yeah.
They just need a temperature difference.
Right.
Something hotter than something else.
Okay, I'm listening.
Yeah.
So where's the hot side of the equation if we're talking about the cold night sky?
The hot side is actually the relatively warm night air.
Okay.
And the cold side is a radiatively cooled surface facing the sky.
So they're using the temperature difference between the air and the sky to generate power.
Yes.
That's mind-boggling.
It is.
And the setup itself is surprisingly simple.
Yeah.
They used a commercially available thermoelectric generator,
Right.
the kind used for recovering waste heat.
Mm-hmm.
This generator is connected to a black emitter designed to efficiently radiate heat into the sky.
Yeah.
And the whole thing is enclosed in a structure to minimize any unwanted heat gain.
Exactly.
And with this simple setup, they actually generated electricity.
They did. It wasn't a huge amount,
Okay.
but enough to power a small LED.
Wait, hold on. They lit a bulb with the coldness of space?
Yeah.
I need a minute to let that sink in.
Oh.
It's like something straight out of a science fiction novel.
It is remarkable.
Okay.
What's even more impressive is that the researchers developed a model to accurately predict how much power the device could generate
Okay.
based on things like weather data and the properties of the components.
Yeah.
This wasn't just a lucky fluke. It was a
Right.
proof of concept.
So this wasn't just some lab experiment.
Right.
They actually showed that it could work in real-world conditions.
Exactly. And they even suggested that with improved components and design,
Okay.
they could potentially achieve much higher power output.
Okay, that's getting into the realm of being seriously useful.
Yeah.
What kind of real-world applications could we see with this technology?
Imagine off-grid sensors or even small devices in remote locations where batteries are impractical or costly to replace.
Right.
This technology could provide a continuous, reliable power source using nothing but the night sky.
This is blowing my mind wide open. We're talking about harnessing a completely untapped energy source.
It is pretty cool.
But hold on, I'm noticing a bit of a theme here.
Okay.
Both of these technologies, the cooling wood and the nighttime power generator, they both rely on this idea of sending heat out into space.
Yeah.
But they're using it in very different ways.
Right.
Almost like opposite approaches.
That's a really astute observation.
Thanks.
One is using radiative cooling to prevent heat gain,
Right.
while the other is using it to create a temperature difference for generating power. It's like two sides of the same coin.
It's like we've been so focused on generating heat and harnessing the power of the sun that we completely overlook the potential of coldness.
And that makes you wonder, what other possibilities are out there?
Right.
What other seemingly impossible energy solutions might be hidden in plain sight?
I don't know about you, but I'm feeling incredibly inspired right now. This is already more than I expected from this deep dive.
Yeah.
I'm ready to keep going. So what else do we have in these sources?
Okay, let's get into it. It really is amazing what we can achieve when we start working with nature instead of against it.
Right. I mean, who would have thought we could use coldness to generate power? But it all stems back to those basic physics concepts.
Yeah.
Like the atmospheric transparency window.
Exactly.
Speaking of which, you sent me a 2016 paper from Nature Communications that takes this idea of radiative cooling to a whole new level.
Okay.
They actually achieved sub-freezing temperatures using just the sky.
That study really pushed the boundaries of what we thought was possible.
Yeah.
What's remarkable is that they were able to maintain...
And they didn't just dip below freezing.
No.
Their cooler stayed at least 33 degrees C below the surrounding air temperature the entire day.
That's insane.
That's crazy.
They even hit a maximum temperature reduction of 42 degrees C.
Wow.
And that was during the daytime,
Oh, wow.
when the sun was at its strongest.
Wait, hold on.
Yeah.
The maximum cooling happened when the sun was blasting down on everything.
I know, right?
How does that even make sense? Shouldn't it be the opposite?
It all comes down to the difference between the air temperature and the dew point.
Okay.
Remember, the dew point tells us how much moisture is in the air.
Right.
When the sun is at its peak, the air heats up quickly.
Yeah.
But the dew point doesn't necessarily rise at the same rate.
Okay.
This creates a bigger temperature difference between the cooler and the surrounding air, and that's what drives the cooling effect.
Ah, so a dry, sunny day is actually ideal for radiative cooling.
Exactly.
That's pretty counterintuitive.
It is.
But wait, how did they manage to block out all that sunlight if they were working during the day?
Right.
Did they build some giant shade structure or something?
They actually created a really clever experimental setup.
Okay.
They used a vacuum chamber with a special window made of zinc selenide.
Okay.
This material is almost completely transparent to infrared radiation in that 813 micrometer range.
Right, our atmospheric transparency window.
Exactly, but it blocks out most of the sunlight.
So they created this controlled environment where the heat could radiate out,
Yeah.
but the sunlight couldn't get in.
Right.
That's brilliant. But, okay, I have to ask, was their emitter some super fancy high-tech material?
Yeah.
Because this all sounds pretty expensive.
Surprisingly, no.
Really?
The emitter itself was a relatively simple layered structure of silicon nitride,
Okay.
amorphous silicon, and aluminum on top of a silicon wafer.
And this was designed to perfectly match that atmospheric transparency window.
Precisely. When they measured the emitter's emissivity, it aligned almost perfectly with the atmospheric transmittance in that 813 micrometer range.
Wow.
It was like a key fitting into a lock.
So they basically engineered this perfect escape route for the heat.
Exactly.
That's pretty amazing. It's
Yeah.
incredible to think how far we've come from those early experiments with simple black radiators just sitting out on a clear night.
I know, it's crazy.
Technology is certainly advanced, but the underlying principles are still the same.
Right.
It really shows you the power of understanding and harnessing natural phenomena.
It does.
You know, speaking of natural phenomena, there's one big one we haven't really talked about yet.
What's that?
Humidity.
Oh, yeah.
You can't really avoid it, especially when you're dealing with something like radiative cooling, right?
You're absolutely right.
Okay, good. I'm glad I'm on the right track.
And luckily, you sent over a 2019 article from Optics Express that tackles this issue head on.
Okay, cool.
They specifically looked at how humidity affects nighttime radiative cooling, particularly in hot climates.
Okay, so this study is getting into real-world conditions because, let's be real, a lot of places that need cooling are also pretty humid.
Exactly. They really went all in on this.
Oh, yeah.
They analyzed a wide range of temperatures and humidity levels from 0 to 40 degrees C and 0 to 100% relative humidity.
Wow.
Talk about comprehensive.
That's a huge range. So what did they find?
Right.
Does humidity completely ruin the party when it comes to radiative cooling?
It definitely plays a role,
Okay.
but it's not a total deal breaker.
Okay.
As humidity increases, the atmosphere becomes less transparent to infrared radiation.
Okay.
That's because water vapor in the air absorbs some of that heat,
Right.
making it harder for it to escape to space.
Right. It's like the water vapor is closing that atmospheric transparency window a bit.
Yeah, exactly.
But the study also found that it's not just about humidity levels, right? The ambient temperature also matters.
You're picking up on the nuances.
Thanks.
For lower humidity levels, higher ambient temperatures actually lead to better cooling.
Wait, so if it's hotter outside but the air is dry, you get more cooling?
Yeah.
I'm so confused. How is that possible?
Think about it this way.
Oh.
Even in dry air, there's still some water vapor present.
Right.
And the warmer the air is, the more moisture it can hold.
Okay.
So even though the absolute humidity might be the same,
Okay.
the relative humidity actually goes down as the temperature goes up.
Right.
This makes the atmosphere slightly more transparent to infrared radiation,
Okay.
allowing for more cooling.
Ah, I see.
Yeah.
It's like the heat is drying out the air just enough to let more of that heat escape to space.
Exact.
But I'm guessing that only works up to a point, right?
You're right.
Okay.
As the humidity levels climb higher, that benefit starts to disappear.
Okay.
In fact, the study found that once the relative humidity gets high enough, it's actually better to have a lower ambient temperature for radiative cooling.
So if it's really hot and humid, you're not going to get as much cooling no matter what you do.
Not necessarily. Even in those less than ideal conditions, they still achieved significant cooling.
Okay.
Remember how we talked about that material used in the nighttime power generator?
Yeah?
The one with the emissivity specifically designed for the atmospheric transparency window.
Yeah, is that 3M enhanced specular reflector film, right?
That's the one.
Okay.
Well, they used that same film in field experiments in Nanjing, China,
Okay.
a place known for its humid summers.
Right.
And even on a hot summer night with 100% relative humidity,
Wow.
they were able to achieve a temperature reduction of 5.2 degrees C.
Wow, that's really encouraging. So even in the most humid conditions, radiative cooling can still make a difference.
And can.
But it also brings up another question.
Okay.
What's better for radiative cooling? A highly selective emitter that's specifically matched to the atmospheric transparency window, or just a simple black emitter that radiates heat across a wider range of wavelengths? I mean, wouldn't a black emitter just blast out heat more effectively?
That's a great question, and one that researchers have been grappling with.
Okay.
The answer, like most things in science, isn't so simple.
Right.
It depends on a lot of factors like humidity levels, ambient temperature, and even the specific design of the cooling system itself.
So it's a trade-off then?
Exactly.
Okay.
In the Nature Communication study we talked about earlier, they found that when parasitic heat loss was minimized,
Sure.
the selective emitter significantly outperformed the black emitter.
Right.
But when they factored in more realistic levels of heat loss, the difference wasn't as dramatic.
Right.
And the Optics Express study highlighted another interesting trade-off.
Okay.
While the selective emitter could reach lower temperatures, the black emitter actually had a higher cooling flux.
Meaning it could move more heat away from the surface even if it wasn't getting as cold.
Precisely. And that suggests that for some applications,
Right.
like passive cooling for buildings where removing a lot of heat is the goal, a black emitter might actually be a better choice, even though it might not reach those super low temperatures.
So it's all about choosing the right tool for the job. And that requires a deep understanding of the physics involved and the specific needs of the application.
Exactly.
Which is why these deep dives are so important.
Absolutely.
But there's one crucial piece of this puzzle that we haven't addressed yet. We've talked about all this amazing potential with radiative cooling, but at the end of the day, none of this matters if it's not affordable, right?
Right.
These technologies could be revolutionary, but they need to be realistic for everyday use.
You're hitting on a crucial point, and I'm glad you brought it up.
Okay, good.
The good news is that cost considerations were a key part of the research we've been discussing.
Okay, cool. So, for example, the Cooling Wood article pointed out that wood itself is already a widely used and relatively inexpensive building material.
Yeah.
So the raw material is readily available.
Right.
And sustainable, which is a great starting point.
And the processes they use to create cooling wood, the delignification and densification, while requiring specialized equipment, are not inherently cost prohibitive.
Okay.
In fact, they highlighted that the incredible strength and durability of cooling wood could actually offset some of the production costs.
Right, because you wouldn't need to use as much material to achieve the same structural integrity, which could lead to savings.
Yeah.
And of course, the energy savings over the lifetime of a building would be significant.
Huge.
Making cooling wood an even more attractive option in the long run.
Absolutely. It's not just about the initial cost. It's about the overall value and long-term benefits.
Okay, that makes sense. But what about that nighttime power generator? That whole setup seemed pretty straightforward.
Yeah.
Using off-the-shelf components. Did they mention anything about cost in that study?
They did. The researchers emphasized that their prototype was built using low-cost, readily available materials and components. They specifically chose commercially available thermoelectric generators.
Right.
And they kept the design of the emitter and enclosure as simple as possible.
And remember, they talked about the potential for even higher power output with some design tweaks and improved components that could lead to economies of scale, driving down the cost even further as production ramps up.
Absolutely. As the technology matures and production becomes more efficient, the cost will likely decrease, making it more accessible for a wider range of applications.
It's exciting to think that these technologies have a real shot at becoming commercially viable.
Yeah.
It's not just some far-off dream.
Right.
There's a clear path to real-world implementation.
That's what makes this field so compelling.
I know, it's so cool.
We're seeing cutting-edge science being translated into practical solutions that have the potential to benefit people and the planet.
It really is a win-win situation.
It is.
So, as we wrap up this deep dive, I have to ask, what was your biggest aha moment from all of these articles? What really stood out to you?
For me, it was the realization that we've been overlooking the most abundant energy source we have access to.
What's that?
The coldness of space.
Oh, wow.
It's always there.
Yeah.
This vast, endless sink for our excess heat.
Right.
And we're finally starting to understand how to tap into its potential.
I know, right? It's like we've been so focused on generating our own heat and light that we forgot about the incredible power of coldness.
It's a fundamental shift in how we think about energy.
Totally.
And it makes you wonder, what other seemingly impossible things are actually within our reach?
Right.
If we just change our perspective a bit.
That's the perfect note to end on, a challenge to our imaginations and a call to keep exploring the unknown.
I love it.
If we can generate electricity using the coldness of space, who knows what else we might discover?
The universe is full of untapped potential just waiting for us to unlock it.
Thanks for going on this incredible journey with us. We hope this deep dive has sparked your curiosity and left you feeling inspired. Until next time, keep exploring.